slower than I expected, so I will be a bit faster now. The next very important paper was again from the Heinrich group from IBM in 2007. They looked at iron on our copper nitride surface that you have seen before. And the nice thing is, there are a lot of steps at zero magnetic field. So in this case, it's a system where it has some orbital momentum L left. It's not totally quenched. There is spin-orbit interaction, which will split the multiplet. And the Hamiltonian is just the uniaxial anisotropy as z square. And in plane, this is a twofold symmetric case. We get these raising and lowering operators to this second order. So this term actually makes a parabola of the states. So S equals 2, we have 5 states. And this operator connects, for example, this state and that state, this state and that state, and this state and that state. So in perturbation theory, that means these two can talk to each other via second order process. And that means these are degenerate states. By this interaction, they will form singlets and they split. This is avoided level crossing that you had also with Wolfgang. And these two can talk to each other, again, singlets, and this one anyhow is a singlet state. So we get 5 non-magnetic states, so we can excite from the ground state with the selection rules we have. From here to there, you can excite, because they are linked already, with the selection rule delta m equals 0, from here to there. Or you can excite from the ground state to this one or that one with delta m is plus minus 1. So these are the transitions. And then in an applied magnetic field, you screw this and you lift this degeneracy, again, this mixing here again, and as function of magnetic field, you can see all these transitions move. This one slowly disappears because this came from this mixing here. And if you have a large magnetic field, now there will be plus and minus 2 states, and there is no direct connection via dipole selection rules. So this state must disappear, and you can see all the steps developing here. And by fitting the energies and the height of these steps, you can find out about the Stevens operators in detail. Now, this still doesn't solve the question, why didn't they see anything in their manganese atom on the bare substrate? And the understanding at that time was the 3D electrons of the manganese, if they sit directly on a substrate, will couple so strongly with the substrate that the spin becomes delocalized. And maybe even classical. And we didn't believe that, so we did an experiment for example, iron and cobalt on platinum. And indeed, we can see in a second derivative now these excitations. And we only considered the diagonal part, and we could measure the anisotropy in this case. Now note that these are pretty broad. The reason is, if I can excite the system with an electron, with a hot electron from the ground state to the first excited level, all of the electrons of the substrate can de-excite the system again to the ground state. They follow the same selection rules. So I can have spin flip scattering with substrate electrons, and there are many. So the lifetimes of these are very short, and they broaden it. This was our understanding. We measured at 4 Kelvin in this case, 4.2 Kelvin. Later, the Wiesendanger group repeated this experiment, and with higher energy resolution, 300 millikelvin, and then you can really see how these states evolve as function of magnetic field. This is for iron. You can see that the steps wonders. This is the simulation for FCC and HCP positions. So the atoms can sit. There are 2 different absorption sites, and this is the measurement. So you can actually determine S and the Stevens operators. Now, to understand, there was a question during the pause, where is the Condor effect? I will discuss that in an example that we measured now for molecules. These are magnetic molecules. You can see this is of C2 symmetry. Here is the SDM image. This is topography. It looks a little bit like C4 symmetry, but if you look at the orbitals with the IDV map, you see clearly this is C2 symmetry. And there's the magnetic impurity here. And the nice thing with the molecules, you can vary the this central ion here. And a side effect is if you are in tunneling, and you approach the tip to this molecule, you place the tip here, you approach the tip to the molecule, you see a discontinuous jump. And if you go backwards, the jump down appears at a different distance. And this is clear, cannot be explained by tunneling. This is actually a deformation of the molecule. When you come close with the tip, there's some interaction, attractive interaction with the tip as well. And so you deform the molecule. And when you deform the molecule, you can directly see the crystal fields might change. And that was the subject of this paper, but I will use it for a different purpose. So this is cobalt as a central atom. And these are the spectra, now recorded at millikelvin temperatures. Or no, this one is still at 800 millikelvins. So what you see is a step here, and then there's this thing in the middle, which was the Condor effect. And I will try to explain you why you have this Condor effect here in this case. What is the Condor effect? I think you have seen it before. It comes from the observation that in metals, if you cool down, I mean superconductors, you know, there's a phase transition, the resistance of the sample goes to 0. And if you have a clean sample, it's expected to be limited by the impurities. These will not go to 0 resistance. But in non-pure metals, actually, below a certain temperature, which is basically the Condor temperature, the resistance increases. And this was largely unknown for some time and was solved by Condor. These are magnetic impurities in the non-magnetic metal. So we have a localized spin sitting in this Fermi sea. And now I will do a second-order transition, a second-order perturbation. I take this electron and put it to the Fermi sea, and take this electron with the opposite spin and put it here. So, as we heard, this is a second-order process. It can only lower the energy, and it actually is lowered by the formation of a Condor state. So a Condor, these are now correlated. They are, let's say, they form a singlet, and this manifests in this peak at 0 energy, which is the Condor peak. And it requires actually that this happens at low temperatures, arbitrary low temperatures. That means to go from here to here should not cost me any energy. If there's an energy difference, then of course this will not happen at low temperatures. So the final state, the intermediate state is an excited state, but the initial and final state must be of the same energy. Now first a remark on when we touch the molecule deforms. This is the first step we observed in the copper. And when we change the Z offset, this is tunneling, and then suddenly this jumps. You can see that this step moves back and forth, which tells you indeed the Stevens operators change, the crystal field change, we're deforming the molecule. This is a direct proof. Well, this one I will take now a little bit more time, is I replaced this central cobalt, nickel and copper. So what we see is, for this case, we have like one excitation and this Condor peak here. This is at 0 magnetic field. And this is now still 800 millikelvin. If we replace it by nickel, we see 2 steps. Although the nickel is, in principle, has a lower spin, we will discuss this, and then we go to copper, and you have to believe me, there is a sharp peak here in the data, and the step here is a phonon, which we could not get rid of. But let's try to understand what's happening here. So cobalt, if you just believe chemistry, a 2+ state is S equals 3/2. We have 4 states. We have this maybe uniaxial anisotropy, dz square. Nickel is S equal 1. You have, again, this term is allowed, the anisotropy. And for the copper, F is S equal 1/2. This has 2 states. And there are no Stevens operators allowed for this case, because the lowest order operators are 2, and you have only 2 states. So S plus 1, 2s plus 1 is 2, and that means n must be larger than 2, and there are smaller than 2. There are no Stevens operators. So this is like a free electron. We can switch. This is in C2 symmetry. We can switch on the allowed term here, which will couple this state to this state and that state to that state. So First of all, I will get one excitation from these. Now these are Kramers doublets. It's a half integer spin. I can go from this ground state or that ground state to the excited states, which will explain the step. Where does the Condor effect come from? Can I go from here to here with a substrate electron flipping? Now this state mixes slightly with this, so this state contains -3/2, but also +1/2. And to go from +1/2 to 3/2 is allowed by spin flip scattering. So that means I connect this state to this state by delta Sz equals ±1. So I will get a Condor effect in this case. It's allowed. So I have a zero energy transitions if there's no magnetic field. And then this, we have this rapid flipping in the simple picture, or in a more complicated picture, we will get a many-body state, and the Condor singlet is at the Fermi energy. If we go to nickel S equal 1, we have 3 states. We switch on the coupling. The coupling couples only this in this state. So raising or lowering operator to the second power. This one is not coupled to anything. That means these are degenerate without magnetic field. They will split. So now we have 3 states and 0 magnetic field. If we are on the ground state, we have 2 excitations. That was our observation. And there's no Condor effect because the ground state is a singlet. Yeah, so spin flip scattering will not play a role here. And we go to spin 1/2. We have these 2 states. They are coupled directly by exchange scattering, and we expect a Condor effect. And that's the picture again. So here we have Condor and 1 excitation. Here we have 2 excitations that you can see here, and you have 1 Condor. And this step, you have to believe, we apply the magnetic field and it does not split, so it's not a magnetic excitation. So what happens if you apply a magnetic field? Now this was the Condor effect. Yes. Now we tilt this level diagram. It becomes this one. So from this ground state to that ground state, there is now an energy difference. We split the doublet. That means the Condor effect should disappear. But I can inelastically excite from this to this, because the Stevens operators mix this and this state, and then there's just one delta M equals 1. This excitation is allowed by the dipole selection rules. And that's what you see here. The Condor is now a zoom, and it was measured at 20 millikelvin. If we apply a magnetic field, this Condor effect disappears, and we get an inelastic step going from this state to that state. And if we apply a magnetic field, now also the other states will split a little bit smaller, and I can go from this ground state to this or to that state by spin flip scattering. And you see this was one step, now this becomes wider and shifted. Now the lifetimes of the states is too short to actually resolve 2 steps. This is smeared, and there should be 2 steps here. And you can see that maybe in this graph again. This is for cobalt again. So you see when we apply the field, if it's small, then you get an inelastic step, but you see these overshoots here. This is the remain of the Condor effect. It's not completely switched off because the energy difference is now small, but it's not small compared to the width, so the lifetime of the states. So the excited state has now a shorter lifetime, and it broadens the energy, and then they still overlap a little bit. So in principle, quasi-elastic processes are possible, but as soon as they go further apart, this disappears more and more. And you can see also the shift of that, of the first step. And you can fit with this all the allowed Stevens operators. Okay. So does this work for 4F atoms? And there was a discussion, and people believed it's maybe not possible, and we just did the experiment, gadolinium on surfaces. What I do here is I use atomic manipulation, so I can move the gadolinium atoms to form here a dimer, and I can record the inelastic spectrum on the dimer. And that's the result. If the dimer sits on platinum or on copper, these gadolinium atoms, they have a relatively low magnetic anisotropy, because in gadolinium is again a half-filled shell. There should be no L, so spin-orbit interaction is small. We have to go to higher order to get a little bit of spin-orbit interaction, so the first excitation is very low in energy. And this one is the, within the, now we have two spins, we couple them by exchange interaction. So you can think of a macro spin of the two gadoliniums, and now I rotate them. I don't break the exchange interaction, but I rotate them in parallel. Or in quantum mechanics, I stay in the same multiplet, and I just change the Z component of this coupled spin system. And the excitation would be by changing one h bar, giving one h bar or taking one h bar of the system, which explains this here. But these are two objects, they are split, they are coupled by exchange interaction, so I can have any state between 2j when they're parallel, or if they're antiparallel, it's 0. So there are many multiplets, and they are split by the exchange interaction. And there's in principle another excitation possible. This is like a miniature magnon in two spins, go from this multiplet to that multiplet, and I have to break the exchange interaction, and that's actually these outer peaks here. And the exchange interaction on platinum 111 is larger than a copper 111. The reason is very simple. The 4f electrons of the two gadolinium are not coupled directly together. They are too localized. They need the conduction electrons to speak to each other via RKKY interaction. And that scales with the density of states. And copper has a relatively low density of states at the Fermi edge. And platinum has a very high density. It's nearly magnetic, so it's very high. So that means the coupling becomes stronger and the exchange becomes larger. Okay. So, but these are all states which are short-lived. So I looked at C2 symmetry. So scattering with substrate and tip electrons may flip the spin. If you want to have a stable state, let's say you want to prepare the atom in the up state, let's say that there are two ground states. In one of the two ground states you want to prepare it. How long does it stay there? So you have to suppress electron scattering. That is, lose either insulating layers or localized spin, take 4f, or maybe in combination of both. And we learned from C2 symmetry that we can either get a Condor effect, that's actually for half integer spins, or we get a singlet state if it's integer spin. So there's only single ground state. So this is not good if you want to store information. If you want to build a classical bit over a qubit. So the only way out is to use higher symmetry, C3, C4, or C6 symmetry. And this is the subject of a paper, or several papers that we submitted or published. And I would like to explain it to you now. I will use the board. I hope my time is good enough. So I want to discuss some symmetries here. So first of all, in this case we have time reversal symmetry. I will come back to that. So that means actually, let's talk in J equals L plus S, because we go to 4f electrons. And what Tj is minus Jt. So it anticommutes with the angular momentum operator. So if I reverse the time, then the angular momentum reverses. That's clear. Or Tj plus minus is minus J minus plus T. If I have a state M, so this is the Z component, if I make the time reversal symmetry, I go, of course, to minus 1 to the power of M minus M. And T square is 1 for J integer, and T square is minus 1 for J half integer. So let's assume we have a state, an eigenstate of our Hamiltonian. Let's say it's a ground state. Then, since T commutes the time reversal operator commutes with our Hamiltonian, I have no magnetic field, zero field splitting, and there are only even terms in J, even powers. That means T and H zero field splitting will commute. So my eigenstates if I have an eigenstate, then I can make a new eigenstate with T of the eigenstate. So psi is an eigenstate. Question is, what is T psi? Let's assume the expectation value, so the expectation value of Jz of this state is not 0. It's a magnetic state. If I use the time operator, then Jz will be negative. So this one will have, let's say this is C. Oh no, I should write it C not equal 0. Then this one will have the expectation value of Z is minus C. So this means we have a doublet. So the time reversal symmetry will make you give you doublets if the expectation value of Jz is not 0. If it is 0, the time reversal state will also be 0. The expectation value of Jz is 0, and you actually are in a singlet. So if the expectation value of Jz equals 0, you have a singlet. This we saw before. There are either doublets or singlets in the problem. Okay, good. This is how we construct our basis. We will take a basis where we have non-zero expectation values of Jz for the doublets, and by definition, all the singlets will have a 0 expectation value for Jz. But we are in CQ symmetry. So Q is equal to 3, 6 on simple surfaces. And we can define an operator R, a rotation operator, by 2 pi over Q. We rotate the system by this Q-fold symmetry. Yeah, if it's C2, we rotate it by 180 degrees. If it's C3, by 120 degrees. C6 by 60 degrees. C4, I forgot 4. By 90 degrees. And since the crystal field Hamiltonian is of this symmetry, and the zero field splitting is also of that symmetry, that means that this rotation operator commutes with the Hamiltonian. So we get a new quantum number, and the quantum number is the phase that the system acquires when we rotate it by the symmetry. So there's a phase, phi is 2 pi m over q. M is the magnetic quantum number, q is the rotation symmetry. So there are states that it's clear.
Why are we doing this? Like, where do you want to go to?
I want to explain you how to get a stable spin.
Okay. So now we try to get the basis.
Well, we have the basis. Before I draw them on a parabola, yeah, and I had some kind of coupling lines here between them. This is too complicated. You will not notice immediately, is this stable, or can I have a zero energy transition between those two states? Yeah, so I want to ask, is this allowed or not? So will I get the Condor effect, or will my spin be stable? And it's not so simple. It's not only half integer and integer. That's for C2, this is like that. So we have a new quantum number, and it's a phase, so we can draw this quantum number on a circle. That's the circle I have here on the image. I can classify my states. I have 2j plus 1 states. I can classify them by the phase they accumulate under rotation. Now, That means I can write my phi as alpha 1 m plus alpha 2 m plus q, and so on. So if I have threefold symmetry, my states mix, and they mix due to the Stevens operator with the power of q here in a raising and lowering operator. So I get a linear combination of this. These are complex states. They are not so easy to calculate. And my time reversal actually means I go from this class to that class. So this would be time reversal. That is just, I go from the phase to the negative phase here. Yeah? There is no x-axis or y-axis. This is the phase. So this is my phase phi. So it's the real and the imaginary part of phi. And the time reversal, my doublets will be kind of on different sides of this. So what is spin flip scattering doing? So spin flip scattering, let's say first the diagonal part, Jz, it does not change the numbers here in the composition. I don't have a raising and lowering operators. I stay with a set of m. So I go from this to the same class. So every state which is in this class can be linked just by scattering with the Jz operator. And the neighboring classes here will be with the J minus or J plus. It should be J plus and J minus like this. So this is this picture here. I can change my phase, my transformation phase with a raising and lowering operator here. We are nearly done. So when will the state be stable? The state will be stable. We want to store information, so it's a doublet. So it's stable when with one electron, let's say these two here, with one electron, they have the same energy. The ground state is a doublet, and they belong, in this case, to different classes related to the time reversal. In this case, I can go with a J minus. So I expect a Condor effect. Yeah. So these two, for example, here in this graph, half integer is here. These two, this is the diagonalization of this problem. These two are linked by the J minus operator. So if this is my ground state doublet, I will have a Condor effect. If this is my ground state doublet, this is the lowest state. Again, the two ground states are of different class. There is no connection with one raising operator or lowering operator or the Jz operator to go from this to here. That means scattering with one electron from the substrate will not flip the spin. It's forbidden. This matrix element is 0. And maybe, how much time do we have? 10 minutes. 10? Okay, good. Then I can explain it. This looks simple, but it's a little bit more complex. So I will show you the protections that are there for your state, the ground state. You have protection by time reversal. So this plays a role for half integer spins, and both ground states belong to the same class. So my ground states belong to the same class. For example, I have two states with this phase here, and they belong to the same class. Then, of course, the raising and lowering operators will bring me away from here to another class. So I cannot go by the raising and lowering operators between the two states with the same phase. So that means, let's say I have two ground states. I call them psi plus and psi minus. This one will be exactly 0 because they belong to the same class. And if I have the raising and lowering operator, I will change the class by 1. So this will be 0. And you can show that also psi plus and jz, psi minus equals 0. Why? These are two objects, and the jz expectation value is different for those two. Yeah? As I said before, these doublets have a different z component, and they're linked by time reversal symmetry. The expectation value of this one will be plus jz and this one minus jz. So the jz operator in between those two must necessarily be 0, because if I this will just give me a positive number of this, and then it cannot be, and this acting on that will give me a negative number, so this must be 0. So that's a particular case where something belongs to the same class and they are still protected. For integer spin, this also exists. So I should make G for the ground state. So psi g minus ji operator psi g plus. I will use the time reversal symmetry now. I will just time reverse everything. So this is this minus. This is identical. Yeah, so I have the time reverse states here, and I complex conjugate this. And then I can change the order of t and j, and I get a minus sign. So this is minus t. So this should be a psi. And now I changed this order of the operators, t, j, I, c, g minus. And now I use t alpha, t beta is beta alpha. So I will reverse the order here again and kill the t. So this will be still a minus here. So this is ji. I write it like this: psi ground state minus, psi ground state plus. And then any Hermitian operator, Hermitian operator, and the components of J are Hermitian operator. Alpha beta is alpha OH beta. So I can reverse the order. So I come to is minus psi g minus ji psi g plus. So that's where we started. That's where we ended. There's a minus sign. So this must be 0. So you can have also integer spins which are protected. Okay, now this is very complicated. You can do the math for everything. So for C2, we had it already. Half integer Kramers doublets, 2 states. They're connected. If it's integer spin, there are 2 classes here. And then you can go from this to this by one. Well, these are singlet states. Sorry, they are singlet states. 5 minutes. Okay, it becomes only interesting if you see this. So this is the order of spin scattering, spin flip scattering. First order of spin flip scattering. If j is larger than 2, then I get, for the phase of plus minus pi over 3, I get something which is yellow, which is protected by time reversal symmetry. That's the case I have here. So I need a spin larger than 2, an integer spin larger than 2, and threefold symmetry. And I will discuss this one here. This is now a C4 symmetry. Again, oh shit, this is not correct. It's here, sorry. Here, then you have a single ground state. So this one should be here. We have a single ground state. And the measurement we did was holmium on platinum. It's threefold symmetric. I now again plot this parabola to make it easy, and the color is the class. We have three classes, C3 symmetry, and this one is a blue state, and this one is a red state. And in principle, you could just spin this is a circle of three, so with the raising and lowering operators, I can go to all states. But this one is protected by time reversal symmetry. And if you do an inelastic scattering experiment, you can see this excitation here, for example. And since we only saw one excitation, we believe that Jz, so J is 8 for holmium, and Jz is plus minus 8 for the ground state doublet. It's C3 symmetry, and this is protected by time reversal symmetry. So if I prepare a state at B equals 0, it will stay in this state. It's forbidden to spin flip with the electrons. If I lift time reversal symmetry, I apply a magnetic field, I will allow inelastic transitions here. So I will, and that's, the experiment says, so this would be a remanence. The magnetic system has a memory, but it has no hysteresis. If you apply a magnetic field, the remanence is lost. And the experiment is done like this. We have a state, we give a short electron pulse, which needs to be higher than this excitation energy here. If I do that, I can inelastically go from here to here, or from here to here, and then the system will relax to this other state. So we can switch by a short pulse the state, and we measure with spin polarized STM that's sensitive to the Z component of the spin in this case. And then you can see, and then we can switch, and then this conduction actually falls back to the same state after some time S. You can make a plot of the residence time, and you see lifetimes T1 times of the order of hundreds of seconds. So we achieved actually 900 seconds for 0.9 Kelvin and 0 Tesla. But if you switch on the magnetic field, so if you wait very long, 0 magnetic field, you just absorb this spin, you see it reverses. This is thermally activated. There are still some excitations in 900 millikelvin. I can go over this barrier, and you can see this spin. So we actually measure a projective measurement of the spin. We can see the single spin here, the statistics. And if you increase the magnetic field, the lifetime becomes short, because we allow this transition now. It's not anymore protected by time reversal symmetry. So that was published in 2013, and in 2017 this was beaten by combining now the idea of isolating the spin of a 4F with an insulator. So this is holmium on an insulator film, MgO, and the lifetimes are extremely long. We have holmium with, again, the ground state doublet is Jz equals mostly plus minus 8 in C4 symmetry. So C4 symmetry, plus minus 8, the difference is 16, is divisible by 4. So the ground state should be a singlet. So this is only stable if you apply a small magnetic field. Then we have this stable. We have very long lifetimes. So at we have T1 times of 5 hours at 1 Kelvin and 50 millitesla. This is extremely stable. So we are going into the regime where quantum computing might be interesting. But so this has hysteresis at magnetic field, but no remanence, because when you are going to zero field, you have the avoided level crossings and the system relaxes. But the first excitation in elastic tunneling spectroscopy basically is at something like 73 millivolts. So these are gigantic anisotropies. In our case on platinum, we only had about 10 millivolts, and here it is 7 times higher. So this is stable up to relatively high temperatures. So 30 Kelvin, you have a stable spin. So at least the last slide that I absolutely need is to tell you that there is a disagreement with XMCD measurements, which has not been resolved so far. So if you take holmium and platinum, you make an ensemble measurement. The magnetization curve cannot be fitted with Jz equals plus minus 8 as the ground state, but Jz equals plus minus 6, which would be not stable. So they did not see any hysteresis, and which is not in disagreement to our prediction, because it has only remanence and not a hysteresis. But anyhow, this is not totally resolved. And similarly, holmium MgO, which should have a hysteresis but no remanence, in the XMCD data has a remanence. And from the XMCD data, the ground state doublet was JZ equals plus minus 7 and not plus minus 8. So there's also a disagreement to the STM data. And at the moment, this is unresolved. How much time do I have? No time anymore, good. I wanted to tell you ESR STM how to get T2 times, but the T2 times are still a problem. They are extremely short. And let me just explain one. You can construct this system. You can make a system which has long T1 times. Let's say we have a state which is up, and we have a state which is down. These both have very long. T1 is very large. It can be hours, hundreds of hours. The problem is what is with the superposition state. So T2 time will make, let's say, this superposition state. And now I just come with an electron. One electron scatters with this state elastically. I will not change the energy. No raising and lowering operators. I will just use JZ. So this is a spin-dependent scattering potential, JZ. So what will happen with this one? We will gain plus 1/2, and with this one we gain minus 1/2, and you will see the relative phase after this is this. And you lost the phase. So that's a problem which is still not solved. So it just takes interaction with a single electron, and your phase is gone. So T2 times are at the moment very short, and this is a measurement by the Heinrich group again, and they measured that like with 60% probability, just one electron will destroy the phase. So it's not yet good for quantum computing. But that is the end of my talk. Thank you. No questions is a bad sign.
Okay, so let's thank once again.
Okay.